Hello everyone, welcome back to LFI Educates. Today we are going to study in continuation with the earlier video, the third video. Here we'll study about combination of resistors. Why do we combine resistors? You'll have the idea because we did in static electricity the combination of capacitors. We try to learn this combination of resistors so that a group of resistors, what function they do, that want to replace it with a single equivalent resistor. That's why we need to know this combination of resistors. And this is very familiar topic to you. You have been learning this in class 10 as well. There are two types of grouping. One is called the series combination. And one is called the parallel combination. When the resistors are connected end to end, then this combination we call it as series combination. Resistor, suppose this is the first resistor, this is the second resistor, this is the third resistor. If you connect it like this end to end, then that combination we call it as series combination. But if the resistors are connected at only two fixed points, all the terminals for the first resistors, second resistor, third resistor are connected at one point, and the other end are also connected at one point. Then this grouping of resistors we call it as a parallel combination. Now let us see what will be the equivalent resistance that we can use to replace the group of resistors both in series as well as in parallel. One at a time let us do. Let us do first for series combination. Suppose the three resistors are R1, R2 and R3. They are connected to a battery or a cell, you can take it. The total potential is V, and as we know that this is higher potential, this is lower potential. Current flows from higher potential to lower potential, or in other words we say conventional current flows from positive to negative to the outer circuit. Suppose the total potential applied here is V, then current will flow through it because of the difference in potential. It will flow in this direction from left to right in the clockwise direction. Now what we like to focus here is whether here the potentials will remain same or different in all the three resistors. There you have to focus first. For R1 you have these two endpoints. Suppose let me say it as A and B. Whereas in R2 it is B and C. Are they the same? One resistor having endpoints A and B. The other one is having B and C. So these two and these two doesn't look the same. These are different positions. So the potentials should not be the same. And the third one, suppose from C to D. So potential will change. And if potential changes, you should know that the current will remain the same. Here also the current will be I, here also will be I, here also will be I. And here the potential will be V1, here will be V2, here will be V3. Across this is across AB, V2 is across BC, V3 is across CD. Now to start with, as the potential changes in series connection, we will write like this. The total potential V is equal to V1 plus V2 plus V3. The net potential of all the three will be equal to the total potential that is provided by the cell. Now, by Ohm's law, we can write V is equal to R into I. Here R is indicating the equivalent resistance for this R1, R2 and R3. Suppose if these three are not in series, only one single resistor, this resistance we are representing it as R, then it will be V, and the current here flowing is I. It will look like this if you replace these three resistors with this single resistor. Then what about V1? Resistance here is R1, current is I. R1, I. V2, the second resistor, here the potential is V2, I into R2, I into R2, and for the third resistor V3 is equal to I into R3 and so on. Now, if you put these values here in equation number 1, suppose this is equation number 1, putting the values of V1, V2, V3 in equation 1, you will get IR is equal to I R1 plus I R2 plus I R3. Then this is IR is equal to I, you can take common from all the three terms, R1 plus R2 plus R3. This II, if you cancel it, you get the equivalent resistance in series combination. Now, if you recall back your capacitors, there in series combination it was reciprocal of the resultant capacitance is equal to sum of the reciprocal of the individual capacitances. But in series connection in resistance or resistors, it is the reverse. Here it is equivalent resistance R will be equal to sum of the individual resistances. You will not do the reciprocal. So it will come out like this. Now, when you see the parallel combination, in parallel combination, your diagram will look somewhat like this. Suppose this is the first resistor R1, this is the second resistor R2, this is the third resistor R3. These are connected at these two ends. Here the potential applied is, you can draw one cell, or you can just show that potential applied is V. This way also you can show. This is positive, negative. The current, it is having branch here, is dividing into three paths. Again they combine together and come out from here and complete the circuit. In this case, all the three resistors are at the same potential because they have two endpoints, A and B, common endpoints A and B. R1 is also connected between A and B, R2 is also connected between A and B, R3 is also connected between A and B. So your potential will, whatever you supply here, it will remain the same. But then what will change is the current. If I is total current, because they are forming branch here, they will get distributed. So here let it be I1, let it be I2 here, and let it be I3, the third branch. So that the sum total of all the three current is equal to I. So to start with, I is equal to I1 plus I2 plus I3. We'll start with this. Now, by using Ohm's law, I is equal to V by R. Here R again indicates the equivalent resistance in parallel. Here, look like this. If these three resistors are connected in parallel, suppose you don't want to connect them like this, together you want to make it as a single resistor, then this will be the circuit, look like this. Then I1 when you say current I1 is flowing across R1, so it will be V by R1, V by R1. Then I2 is equal to V by R2, I3 is equal to V by R3, and so on. If more than 3, then we'll go on. Then if you mark this as equation number 1, like the earlier case, we'll put the values of I, I1, I2, I3 in equation number 1. Putting the values of I, I1, I2, I3 in equation 1, you'll get the expression I is equal to V by R, that is equal to V by R1 plus V by R2 plus V by R3. Then here we can write this as V into 1 by R, separate this V from here. Then the other three cases V you take common, 1 by R1 plus 1 by R2 plus 1 by R3. Then this VB, if you cancel it out, you'll get the equivalent resistance in parallel, plus 1 by R2 plus 1 by R3. From here, you can find out this equivalent resistance in parallel. In the second case, this will be in parallel, the earlier one was in series. There you can write RS. Now if you look back with your capacitor, capacitance of the capacitor in series, to find out, we did like this: 1 by C1 plus 1 by C2 plus 1 by C3 and so on. We got like this. And 1 plus C2 plus C3. But in case of resistors, it is just opposite to that. In series, resistors in series, you got R1 plus R2 plus R3, and the resistors in parallel, the equivalent resistance was reciprocal. It's reciprocal. Just now we did R1 plus 1 by R2 plus 1 by R3. Let's note it nicely. Sometimes it creates confusion while solving the numericals. Now, yeah, these things you did in lower classes, so it won't take much time for you to understand it. Now let us talk about electrical energy and electric power. Electric energy. Electric energy is defined as the amount of work done by the source of electricity. Our source of electricity is our battery, to allow a steady current to flow for a specific period of time. Now, electrical energy, when you say, we can get the expression like this: by Ohm's law, definition of current, you can write I is equal to V by R. Then by the definition of electric current, by definition, we all know that current I is equal to charge that flows per unit time. And also we know the work done. Now we said electric energy is the work done by whom? By the cell, to allow current to flow, steady current to flow, or to allow the steady current to flow in the circuit for a specific period of time. So work done, W is equal to charge into potential. This one comes from the definition of potential difference. It is the amount of work done in bringing charge from one point to another point. So work done is equal to potential into charge. So with these three expressions, if you remember, then you can get the expression for electric energy. Put the value of Q from here. Q is equal to I into T, and V is equal to I into R. So it will give you I square RT. This work done is stored in the system, that is in the circuit, as electric energy. So we write energy or work done energy is equal to I square RT. This is the first expression that you can get. The other two expression for electric energy you can get like this. E is equal to I square. R is equal to, use your own law, R is equal to V by I. V by I into this is T. So I one time if you cancel it, you will get VI T. This is V, this is I, and this is T. So this way also you can express electric energy. The third way to express electric energy is E is equal to, here I square. What is I square? V square by R square. V square by R square. Then R into T. R into T. So this one time R, if you cancel it, you will get a third expression for electric energy. V square by R into T. Likewise, we can get all the three expressions for electric energy. Okay, this one, let us write the reason why we got like this. Since R is equal to V by I, what we have substituted, where R is equal to V by I. Here, in this expression, we have substituted I square is equal to V square by R square. Then we got like this. Electric power. Electric power is defined as, we simply represent it with P. It is defined as the electrical work done per unit time. Generally we know that power is equal to work done per unit time, and work done is a measure of energy. So we can say it is energy per unit time. So electric power P can be written as, from this three expression, I square RT, the first expression, I square RT, simply divided by T, then you get the expression for electric power. It's I square into R. This is the first expression. And the second expression, power, can also be defined as V into I divided by T. This time won't vanish. So V into I. And the third expression for power will be here, V square by R. Power is equal to V square by R. These are the three expressions for electric power. Here among these three, this expression, that the first expression that we got for energy, we even call it as Joule's heating effect. This is also known as heat energy in electricity. The resistance offered by the wire will make the object hotter, and how much heat energy is produced by the appliance, that you can measure it with the help of this product of I square R and T. This is also known as Joule's law of heating. In that case, this energy, we'll write it as heat energy H. It is equal to I square R T. Heat is produced because of the presence of resistance. It is directly proportional to resistance. Don't make mistake here. This resistance is inversely proportional. This downside will not take this expression. We'll do with this expression if they ask you to find out the heat energy. Now let us talk about their units. Electric energy. Energy, as it is the amount of work done. The SI unit of electric energy is also Joule. SI unit of electric energy is Joule. Other higher units we use sometimes, like kilojoule. We use it as kilojoule. Kilo means 10 power 3. 10 power 3 joule. This 1000 joule is equal to, 1000 joule is equal to 1 kilojoule. When you say 1 kilojoule, kJ we write is equal to 1000 joule, or we write less than power 3 joule. Then the commercial unit of energy is kilowatt hour. Kilowatt hour. This is the commercial unit of energy. Is 1 kilowatt hour. 1 kilowatt hour is equal to 1 into kilo means 1000 watt into 1 hour. This is 1000 watt into 1 hour is equal to 60. Each hour is made up of 60 minutes and each minute is made up of 60 seconds. So it will be 1 hour equal to 60 into 60 seconds. Joule per second. You can know from here, work done is joule and time is in second, into 60 into 60 second. Second if you cancel it, 6 6 are 36 into 10 to the power 1 2 3 4 5 zeros joule, or we can write more nicely as 3.6 into 10 to the power 6 joule. So this is 1 kilowatt hour, we write 1 kWh as well. This is the commercial unit of energy, and 1 kilowatt hour is equivalent to 3.6 into 10 to the power 6 joule. Now let us see the SI unit of power. SI unit of power is watt. 1 watt is equal to 1 joule divided by 1 second. The joule per second is watt. When 1 joule of work is done for 1 second, then the unit of power is said to be 1 watt. Other higher units of watt is kilowatt. Kilowatt. When you say 1 kilowatt, it is equal to 1000 watt. That is equivalent to 1 kilowatt. And the other unit of watt we use is unit of power is horsepower. 1 HP we write. 1 horsepower is 746 watt. These are used for making heavy machines like crane or vehicles. Then the power is measured in terms of horsepower. Let us do some numericals now. Here is one simple numerical on the board. The three resistors with resistances 2 ohm, 3 ohm, 5 ohm are connected in series with 10 volt battery. The battery is of 10 volt. Calculate the equivalent resistance. That means if we group them together, what will be the equivalent resistance we have to find out, and current that passes through each of them. Now to do the solution, current will be the same because it is in series. So everywhere the current will remain the same. Here the difference is the potential. What we will do, first of all, the equivalent resistance to find out in series. Equivalent resistance, you can write this RS, it is R1 plus R2 plus R3. Then add them up, 2 ohm, 3 ohm and 5 ohm. How much it will be? 8, 9, 10 ohm. So you will get the equivalent resistance in series. Now overall, your 3 resistors, you are making it into a single one, it is 10 ohm. Now this is your battery with 10 volt. So what will be the net current? You can find out the current flowing through the circuit. So by Ohm's law, I is equal to V by R. Potential is 10 volt. Resistance is 10 ohm. So it will be 1 ampere. So the amount of current flowing through each resistor will be 1 ampere each. In the given network, three resistors 2 ohm and 4 ohm are connected in parallel with a 12-volt battery that you can see here. Determine the equivalent resistance and current through each resistor. When you do the solution in parallel, the reciprocal of the equivalent resistance in parallel is equal to sum of the reciprocal of individual resistances. So 1 by R1 plus 1 by, first you can write in the formula, R1, 1 by R2 plus 1 by R3. Then 1 by R1 is 2 plus 1 by R2 is also 2 plus 1 by R3 is 4. LCM will take 2, 2 and 4, LCM will be 4. 2 2 times plus 2 2 times is 4 plus 4 1 time. So it is 4 5 by 4, or RP is equal to, reciprocate it here also, reciprocal of 5 by 4 will be 4 by 5. So the equivalent resistance Rp is equal to, if you divide it 0.5, it's a 40 ohm. Like this you can find out the equivalent resistance. Then in case of current, if current, the total current flowing through the circuit you can find out first of all. The total current, if you use Ohm's law, by Ohm's law, current I is equal to V by R, resistance here combination, this one is 0.8 ohm. So V, the potential is 12 volt, divided by combination of resistor, it is 0.8, 12, the decimal one is 0 divided by 8, 8 ones are 8, 8 fives are 40. Yes, so the current I is equal to 15 ampere. The total current is 15 ampere. But now we know that in case of parallel, in each branch the current will be different. Let it be I1, this is I2, and let it be I3. So one by one we'll find out. Current through the first resistor is R1. Let us write it as I1. I1 is equal to, by Ohm's law, I is equal to V by R. The potential here remains the same because it is connected in parallel. Total potential is 12 volt and resistance, it is 2 ohm. Total potential is 12 volt. V by R1. V is, total potential is 12 volt divided by R1 is 2. Yes, resistance is 2 ohm. So it will be V by R1. This is 6 ampere. Then current through R2. So write I2. It is V by R2. V is 12. R2 is also 2 ohm. So it will be 6 ampere. And current through R3, this I3 is equal to V by R3 is 12 divided by R3 is 4 ohm. 4 3s are 12 ampere. This one, the purpose of finding out total current is to see the 6, 6, 12, 12 plus 3 is 15. So mention this total current 15. This 15 ampere current will flow through R1, R2, R3, and as they are dividing it among themselves, here 6 ampere, here 6 ampere, and here 3 ampere will flow. Let us solve these questions. Find the equivalent resistance between points A and B in the circuit given below. Here 3 circuits are there. All are, the resistors are connected between A and B, A and B, here also A and B. Let us do one by one. Here, in this type of circuit, we have to judge whether the currents are distributed or the same current is flowing. If you see a junction, then if the currents are distributed, then you come to know that it is in parallel. Here, let us look here. Suppose the current is coming from point A, then it has got two branches. So this current will get distributed here as well as here. Let's just take it as 10 ampere. The current, just for understanding. Then suppose here 2 ampere goes and here 8 ampere goes. As an example I am taking. Then here the currents are not the same. If this 8 ampere current will go and reach here, is coming 8 ampere. Then this 2 ampere, suppose say here it is going, again branch is there, so 1 ampere, here also 1 ampere. This 1 ampere, it will come from here, 1 ampere plus 8 ampere will be 9 ampere. Then here 1 ampere current is flowing from the top. So here 1 ampere and this one 9 ampere coming from here, all together will become again 10 ampere. So 10 ampere, if you allow it to go, 10 ampere should come out on the other end. So if you look very carefully here, across this resistor, current is 2 ampere. Across this resistor, current is 1 ampere. Across this resistor, current is 9 ampere. That means in all the three resistors, the current flowing is not the same. Then you come to know that the three resistors are connected in parallel. Now, since the three resistors are connected in parallel, the equivalent resistance, this is the first one we are doing for the first circuit diagram. The equivalent resistance in parallel will give 1 by Rp, that is, or equivalent EQ also you can write. This is 1 by 2R plus 1 by again 2R plus 1 by R. If you take LCM, 2R will come out as the LCM. 1 plus 1 plus 2. This is 4 by 2R. 2 times is 4. So the equivalent resistance in parallel will be R by 2. Reciprocate it. 1 by Rp, reciprocal is Rp. So likewise you can find out the equivalent resistance, and this is the way to judge whether the same current is flowing in all the three resistors or different current is flowing. If same current is flowing, then the connection is in series. If junction is there, is distributing, then you should know that they are connected in parallel. Let us see the second one. In the second case, same way how I say it, it's not necessary that you have to write the amount of current. Any value you can take and do. Suppose from here A, current is flowing. Suppose current is coming from this way. Then this is a junction, you can see. It will get distributed. That means these two are not connected in series, it is connected in parallel. But what about this? What current is flowing here? There is no junction, it's just a band only. Same current is flowing through it. So these two are connected in series, and this one is connected in parallel with both of them. Because here also again junction is there. Just here also just take it as 5 ampere of current. Here 2, here 3 got distributed suppose. Then 2 ampere of current flowing here, 3 ampere of current coming from here, 2 ampere and 3 ampere together will become again 5 ampere. So these two are in series, and with this it is in parallel. So this one you can draw it like this. We draw the diagram like this. This we are doing for the second one. 20 ohm and 30 ohm. 20 ohm and 30 ohm are connected in series. But in turn, the 50 ohm is connected in parallel. Like this it is. And these two ends, one is end A and one is end B. It is like this, you can redraw it this way. So in series, the equivalent resistance like this you can do and represent, we are finding out for this. Equivalent resistance in series RS, will write 20 ohm plus 30 ohm, it is 50 ohm. Then after these two got combined together, then your circuit will become somewhat like this. These two together it became 50 ohm, and then the other resistor is already 50 ohm. It's like this now. This is A and this is B. So now for parallel, you can do like this. Resistance in parallel, reciprocal of equivalent resistance in parallel. It is, that will be your equivalent resistance ultimately now. Equivalent resistance. It will be 1 by 50 plus 1 by 50. So 50 is the LCM. 1 plus 1 is 2. It is R equivalent. R equivalent, you can write it as 50 by 2. It is 25 ohm. And like this you can find out the equivalent resistance. Now let us see the third diagram. Let us redraw the diagram here and then do the solution. The third one. One resistor here, one resistor here, one resistor here. This is the combination given. This is A, this is 8 ohm, this is 4 ohm, this is 1 ohm, this is 3 ohm. Now here also the current is flowing this way from A, suppose the same amount of current won't flow through 4 and 3 ohm because branch is there to get distributed. But what current flows through 4 ohm? The same current will flow through 1 ohm also because there is no branch, it is just a band. So in this case, you will find out like this. These two are in series, end-to-end connection. So first you write like this. Resistance in series is equal to 4 ohm plus 1 ohm. It will be 5 ohm. This one do it first. After you do this one, you got a single resistance. Now together with this, it is in parallel. You can draw the diagram together. You got one. You can draw here or you can draw here also. These two are in parallel. So we'll do like this. This is A. This is B. This is 8 ohm. Then there is a branch here. 3 ohm. Come like this, and this one you can keep it this way. How much we got? 5 ohm. Now as these two are in parallel, how do we know that it is in parallel? Because here the current will get distributed. In both the places the amount of current will not be the same. So here you get like this, 1 by Rp is equal to 1 by 3 plus 1 by 5. 5, 3, 15 LCM, 5 plus 3, this is 8 by 15. So Rp is equal to 15 by 8. You can divide or you can keep like that. You can keep this way also, 15 by 8. Now these two together, it has become a single one. Now it will be in series with 8 ohm resistor. The third case, you can do like this. These two grouped together, you got 15 by 8 ohm. So it will look like this. This is A. This is 8 ohm. And now you have 15 by 8 ohm. So this will be the ending point B. Or if you bring like this also, B will be here. Same thing, the same wire. Now here it will give you the equivalent resistance. Therefore R equivalent is equal to 8 ohm as they are in series. 8 ohm plus 15 by 8 ohm 8 is the LCM, 64 plus 15, 79 by 8 ohm. Like this you can find out the equivalent resistance. Two bars of radius R and 2R. One can see of radius 2R and one is of radius R. These are the two bars AB and BC. Are kept in contact as shown. An electric current I is passed through the bars. You have to find the ratio of heat produced in the bars AB and BC. First of all, as these two rods are connected in series, the amount of current flowing through it will remain the same. Solution to start with, the current flowing through both the bars are same as they are connected in series. As both the bars are connected in series, then the amount of heat produced, they are asking for a ratio of heat produced. Heat energy H, we know that it is equal to I square RT, and heat energy H therefore is directly proportional to the resistance. Is directly proportional to the resistance. Let's start like this. We know that H equals to, like this you can start. So heat produced by the wire AB divided by heat produced by the wire BC will be equal to, as it is directly proportional to resistance, resistance of the wire AB divided by resistance of the wire BC. Then again, resistance is inversely proportional to the square of their radius. 1 by 2R squared divided by 1 by R squared. Like this you can show resistance is inversely proportional to the area of cross section, and so area of cross section, when you say it is directly proportional to radius, so the answer will remain radius square 1. So ultimately resistance is inversely proportional to square of the radius. So with this you can write like this, then calculate it. 1 by 4R square, this one 1 by 2 square is 4R square, into this one we have to reverse it, R square by 1. Then R square if you cancel it, you will get 1 by 4. So it is 1:4. Like this you can calculate it. Thank you and have a nice day, and wait for the next video to come out. That is, it will be video number 5 in this chapter.